Hello everyone, welcome to this presentation. My name is Long Zhang and currently I'm doing my PhD study at KTH, Royal Institute of Technology in Sweden. Today I'm very happy to present some of our research work on chaos engineering. This is the journal first paper, which was originally published in TSE last year. The title of this paper is A Chaos Engineering System for Life Analysis and Falsification of Exception Handling in the JVM. So before introducing the concrete research work in this paper, I would like to briefly introduce chaos engineering first. Nowadays, there are lots of complex software systems. After deploying such a system in production, it is challenging to predict all kinds of failures. And it is also challenging to analyze the system's resilience against these failures. One idea is to change our perspective of failures. Instead of being worried about them, we actually inject failures actively in a production-like environment so that we can learn more about how our system behaves when such failures happen. By learning from failures, we can improve the system's resilience in the future. Chaos engineering is such a technique that injects failures on purpose. It is the discipline of experimenting on the system in order to build confidence in the system's capability to withstand turbulent conditions in production. Because this is done in production, we have to follow some of the principles. For example, we need to define what is the normal behavior of our system before conducting any experiments. We also have to control the blast radius, because an experiment in production potentially has some side effects on user experience. So we have to minimize these side effects while still learn as much as we can about the system's resilience. To be more specific, in our paper, we would like to explore how to apply chaos engineering to get a unique and actionable analysis on exception handling capabilities in production at the level of try-catch blocks. In this paper, we call this chaos engineering framework ChaosMachine. As an overview of ChaosMachine, it takes two different kinds of inputs: arbitrary software in Java and a set of hypotheses. There are three kinds of components in ChaosMachine: monitoring sidecar, perturbation injector, and the chaos controller. For each of the target Java application, there is a monitoring sidecar and a perturbation injector attached to this JVM instance. Both of them are controlled by the chaos controller for conducting chaos engineering experiments. The monitoring sidecar is responsible for collecting different levels of metrics. For example, it can collect performance-related metrics such as memory usage and CPU usage. The monitoring sidecar are also monitoring some application-level metrics, for example, the HTTP response code for web applications. The perturbation injector injects Java exceptions when it is activated. The chaos controller orchestrates the other two components to conduct experiments and outputs a resilience report and relevant monitoring logs for developers. In order to inject exceptions in a systematic way, the perturbation injector relies on perturbation strategies. This could be defined by developers based on their experiment goals. By default, we propose a perturbation strategy that short-circuits a try block. It means that the injector injects a corresponding exception at the beginning of a try block. In this case, we make the whole try block invalid, and the code in the catch block will be executed when an exception is injected. This could be helpful for developers to evaluate a catch block's error handling capabilities in a worst scenario. A catch block could be considered as a good recovery strategy if it still makes the system provide acceptable functionalities. Regarding the experiment hypothesis, we propose the following four for our evaluation experiments. The first hypothesis is resilience hypothesis. It means that when we inject an exception, the observable behavior of the catch block is equivalent to the observable behavior of the try block. In other words, This catch block is still able to provide correct functionalities for end users when an exception occurs. The second hypothesis is observability hypothesis. It means an exception caught in the catch block results in user-visible effects. For example, if ChaosMachine injects an exception which crashes the application, the user is aware of this exception. The third one is debug hypothesis. This one is relevant to debugging mechanisms. When an exception is injected, the system generates an explicit message in logs, so developers can have more information about such exceptions. The last hypothesis is silence hypothesis. When an exception is injected, the system fails to provide the expected behavior upon exception while providing no troubleshooting information. It is not observable either because the user cannot be aware of these exceptions. So based on this hypothesis, what can be learned after doing chaos engineering experiments? First of all, developers can learn more about the resilience of the target system with respect to exceptions. They can fix the silent catch blocks if necessary. They can also gain confidence about the error handling capabilities in the resilient catch blocks. Developers can also know more about log handling mechanisms. For example, whether sufficient information is recorded when an exception happens. To evaluate ChaosMachine, we selected 3 representative Java applications on GitHub, including a file downloading client, tTorrent, a commercial website application, Broadleaf, and a popular wiki system called XWiki. In this presentation, we use tTorrent as an example. tTorrent is a good open source project which has more than 1,000 stars on GitHub. It is also easy for us to have a real production environment and traffic. The results show that ChaosMachine successfully detects 52 try catch blocks. 27 out of them are covered by our workload. There are also 6 possible resilient catch blocks. ChaosMachine also identifies 3 silent catch blocks. Such results bring more insights about the system's resilience to developers. For example, each silent try-catch block indicates a potential debug case that would be extremely difficult to fix because there is no visible behavior. No log can be provided by the user either. As a summary, in this paper, we mainly have the following 3 contributions. We propose the conceptual foundations of chaos engineering in the context of exception handling in Java. We also implement a novel system called ChaosMachine that assesses error handling capabilities in production. We also conduct an empirical evaluation of ChaosMachine on 3 real-world Java systems. So if you feel interested in ChaosMachine's source code and our experiment results, you are more than welcome to take a look at our Royal Chaos GitHub repo. It is a mono repo which contains lots of our research work in the field of chaos engineering. Lastly, a few words about the future work of ChaosMachine. We think that would be interesting to explore an advanced perturbation strategy for the Perturbation Injector. It could be also interesting to enhance the monitoring sidecar so that we can capture more sufficient information and also calculate the steady state more precisely. So here are some citations of the related works in the field of chaos engineering, not only done by our group, also done by the other researchers in the world, just to show that the research on chaos engineering is moving in academia. Alright, I think that's all for my presentation today. Thank you once again for listening, and I look forward to your comments.
Welcome to everyone. Next session is Programming Low Level. We have 3 papers in this session. I'm Ignacio Panac from University of Valencia, Spain, and I'm going to chair this session. So the first paper in this session is called a chaos engineering system for live analysis and falsification of exception handling in the JVM and the author is Long Zhang, that he's here to answer any question you would like to ask.
Hello,
So
everyone.
please use the chat on the right of the window to ask any question to the author. In the meantime, I have several questions for you. So the first question is, you say that the output is a report and monitoring logs. What is the template that you are using for the output?
Yeah, thanks, Ignacio, for the organization and the questions. I think it might be better to share the screen so I can show you the template we are using.
Okay, perfect.
Yeah, thank you. So actually, this is one of the tables in our paper, like the results of our chaos engineering experiments on one application. And we tune the format a little bit, but basically the format of our like a generated report is something like this. Like we report the execution, the number of executions, like whether we have already captured logs, whether some application-specific metrics, like for example, whether it crashes or whether it successfully download the file, if the application is a file downloading client, etc. And then finally, we provide like 4 hypotheses, whether they are falsified or verified in this experiment. And the corresponding logs are directly captured from this specific application. So we don't have like a unique template for that one. But for reports, it looks like this one.
So even if you don't have a template, the information that you display, just the information that you are you are showing in this table, right?
Yeah. The original output is a CSV file, which contains these columns.
Okay. And you consider 4 hypotheses: resilience, observability, debug, and silence. I would like to ask which one of these hypotheses you consider that is more relevant in your approach.
Yeah, thanks for the question. For me, I think because chaos engineering is more about like evaluating an application's resilience in a production-like environment. So I think resilience hypothesis for me is like the most relevant one in chaos engineering and in my research work. The reason is I think this could be a really good sign for developers if the hypothesis is verified, because it confirms like the developers are like they are able to successfully design some, for example, second error handling strategy in their catch block. So if the resilience hypothesis is verified, then they gain more confidence about their error handling logistics. If this hypothesis is falsified, then we can learn more about the failures and the information from our chaos engineering experiment. But of course, I think silence hypothesis is also very interesting because it provides like a pretty few information for debugging. So we can pay more attention to these like track catch blocks which broke the silence hypothesis.
Okay. And my next question is related with the previous one. It's not what do you think that is more relevant, but what do you think that is the more frequent on the systems? Because maybe from these 4 hypotheses is one that is more present in real systems.
By frequent, you mean like which hypothesis will be verified or falsified like most times? That's
Yes, the hypothesis that is more satisfied
common.
in.
Okay, I see. Then I think I can also share the table in the paper, because from this like a summary information, we can see the debugging hypothesis is like satisfied in most of the time. So I think we can have like more information about whether injected exception is logged properly logged in their like logging system. So it can provide some more debugging information.
Okay. My next question is about conceptual modeling. I would like to know if in your approach you could apply a conceptual model proposal such a way you can think in the problem and not on the solution. You think that a conceptual modeling approach could be suitable also in this work?
You mean modeling of the errors? For
Yes.
example, yeah, at the level of source code or before the deployment, right?
No, before.
I see. That's a really good question, and I think it's a really helpful for each other, because for chaos engineering it does more experiments at runtime in like a production environment. But one of the challenge is how to properly find the hypotheses. So that's why we provide this exploration experiments to help developers find more hypotheses. But if we apply some modeling techniques before the deployment, it will be super helpful for chaos engineering experiments, because we can gain more knowledge about the system and we can define realistic hypotheses for the target system. So I think it could be helpful, and it could be a combination of this one, because something we might need to verify the system at runtime. For example, the Java's like a class loading feature. Some of the classes might not be different if we analyze the source code, something like that. So I think it could be very helpful and interesting for us to
Okay.
explore this. Yeah.
And my last question is about your next step or your future work. What are you thinking to do in next months to continue with this work?
Yeah, thank you. I briefly mentioned we have I shared some papers which are not only done in our team but also by other authors in the field of chaos engineering, and I think for me one of the interesting direction after ChaosMachine, after this paper, is to explore, for example, the cascading failures or cascading exceptions, because when we do this chaos engineering experiments, we consider all the try catch blocks separately. So if one exception is thrown from one try block, and this exception is thrown in their catch block again, so we catch the exception but throw it again, then for ChaosMachine it becomes two separate experiments. But it will be interesting to see how these exceptions influence each other, and to have this propagation chain of the exceptions in the target system. So I think that's quite interesting for us to try. It's also related to
Okay.
advanced hypothesis, I think.
So thank you very much. It's a very interesting work. So
Thank you very
congratulations.
much. Thanks.
So if there is no more questions from attendees, we can just give you a virtual clap for all the attendees.
Thanks a lot.
And if
Thanks
any
everyone.
attendee would like to talk with you directly, you can go to the discussion room, and there you can find Long, that who will here there, just in case you would like to talk directly with him.
Yes.
Okay, so congratulations, Long.
Thanks.
Very,
Thank
very
you
good work.
again. Extensive. Yeah.
See
Thanks
you.
everyone for listening.
Welcome